Okay, so today we're going to kind of go over the entire 12.3 lesson, which is all about what's called the tangent line problem. So what's really cool about this tangent line problem is it's kind of the basis of calculus, which is what you're going to take next year. So basically what we did at the beginning is we just talked about what is a tangent line, and a tangent line is a line that passes through a graph at one point and then it moves on. That's what a tangent line is. So what's really, really cool about this tangent line problem is it's basically asking, can you figure out the slope if you only know the equation of the line and a point? Traditionally, if we're thinking about what we know in mathematics so far, we know how to find a slope using 2 points. But to find a slope just using 1 point and an equation, we probably don't know how to do that quite yet. So we're going to talk about how can we connect limits to this tangent line problem. All right, so let's go ahead and let's keep going. First thing we did is we talked about visualizing and approximating slopes using a graph. So what we did is we drew tangent lines at each of these points and we approximated what we thought the slope was. For example, this slope we thought was probably about 4. This slope right here, we thought maybe that's -2. And you can see that any slope that happens on a vertex or happens on a max or min, you can see that the tangent line is horizontal and you're always going to have a slope of 0, which actually has huge implications for calculus later. But I'm trying to keep this video brief, so we won't go over that quite yet. All right, so the next thing we're going to talk about is this is it. This is the big question of calculus, which is this. If I have a point, and say that our point is, I shouldn't fill that in. Say our point's this red point right here. And we want to know, hey, what's the slope of the tangent line at this point? To find the slope of the tangent line at this point, we can actually find it by thinking about the secant line. Now, the secant line is a line that goes through 2 points. So tangent goes through 1 point, secant goes through 2. And the tangent line maybe looks something like this. The secant line does. And so the secant line, I actually know pretty well how to find the slope of a line with 2 points. That's y2 minus y1 all over x2 minus x1. And basically, I can actually use the secant line to approximate the tangent line. We talked in class and talked about how the secant line in this particular example, it looks really close to the same slope of the tangent line. And the fact of the matter is that it is really close to the slope of the tangent line. What I want to do is I want to make it as close as possible to the slope of the tangent line. And the best way to do that is to take these 2 black points and move them closer to the point that we're looking for, the slope of the tangent line. If I make these 2 secant points really, really close to the red point, then in theory, I should be able to find the slope of the red point. So what we did in class is we went ahead and defined the black point, the 2 black points, to be x, comma, f of x. And after that, we went some distance. And I think some students decided that our distance, we're going to call it q. So we went some distance to the right. So our next ordered pair is actually just going to be x plus q, comma, f of x plus q. And then what we did is we just used the equation of that finds slope for us to figure out what the slope of the black line will be. So if I use y2 minus y1 all over x2 minus x1, we're going to find the equation of what we think the slope of the black line should be. Well, to find the slope of the black line, we're going to do y2, which is f of x plus q, minus y1, which is f of x, all over x2, which is x plus q, minus x, which is x sub 2. We can see here these 2 x's are going to cancel, and so we're just left with q in the denominator. Now, what's really cool about this is we've seen this expression before. Maybe you don't quite remember it, but we have seen this before if we replace it with h. F of x plus h minus f of x all over h. We know that expression. We've done that a bunch of times in previous lessons, and maybe we didn't have any context for it, but what this is saying is that this tells me an approximation for the slope of the tangent line. The only thing that I need to add in is that we want q to be super small. The smaller that the distance is between these 2 points, the more close of an approximation we're going to get to the tangent line. So if I make Q super duper small, I can make it like 1, which is decently small, or I can make it 0.1, or I can make it 0.0001. If I make it something really close to 0, in fact, we could actually say approaching 0, then I could write that in form of a limit. I can write it as the limit as Q, in this case we might say x2, approaches 0. So we're saying that the distance between these points is infinitely small. It approaches 0. This entire expression, the limit as Q approaches 0 of f of x plus Q minus f of x all over Q, this is the slope of the tangent line. So this limit approximation is the slope of the tangent line, which is so cool because we've been working on these problems this whole year, and you maybe didn't know that you were actually finding the answer to the tangent problem. You're actually finding the slope at a moment, which is super cool. So we're going to go and talk about what that means. Number one, if you just want to know what's the definition of the slope of a graph at a moment, you could also say the slope of a graph at a point. So at a point. This is the equation for it. It's what we've been doing this whole time. Limit as h approaches 0 of f of x minus f of x plus h minus f of x all over h. These are the same thing. If we write, if I want to find the slope of the graph at a moment, I need to use the limiting process. So let's go ahead and practice. I know these look like crazy problems here. They're really the same problems that we did yesterday, so I'm not going to go over them too much. Just know that it's probably for the best that you would use a highlighter to highlight f of x versus f of x plus h. If you simplify and cancel h, each time your result is actually going to tell you what if I can write on here? Your result each time is going to tell you what the generic slope is at any point. So anytime that I do this limiting process, I'm actually coming up with an equation that tells me the slope of a graph at any point, which is a really amazing thing to do. So let's go ahead and let's keep moving. Finding the formula for the slope of a graph. So imagine that I'm given the limit as h approaches 0 of x plus h quantity squared plus 1 minus x squared plus 1 all over h. We can actually use that information to find out exactly what the original function was. And in this case, the original function is actually x squared plus 1. And you can actually see it's always in the subtracting term. Same thing here. If we take the limit and we take a look at it, we can actually find the original function by looking at where we subtract. The thing we subtract is actually the original function that we're looking at, which is pretty cool. All right, so let's keep going. All right, let's keep going. So the next one. You might see this word a lot when you start asking anyone about calculus. It's one of the big buzzwords in calculus, and it's the word derivative. Derivative is really just code for slope of a tangent line. So the biggest thing we need to know when it comes to the definition of a derivative is probably the limit, but also that it is the slope at a tangent line. Now, we just talked that the slope of the tangent line is this limit. It's the limit as h approaches 0 of this whole thing. So basically, when I say the word derivative, what I'm really asking for is what's the slope of the tangent line. And to find that, we need to use the limit. Some notation that you might see for derivatives, the most common one you're going to see is f, what's called prime of x. So your most common notation you're going to see is f prime of x. All right, so let's go and practice. So say if I want to find the derivative of 2x squared plus 3. To find the derivative of 2x squared plus 3, all we need to do is plug it into the limit process, and we actually end up with 4x. In class today, we actually talked that there is a pattern to finding these. I'm not going to tell it to you on this video, but if you want to look it up, there is a pattern that's a lot faster than the limiting process, but I want you to find it out on your own. So we actually, I think we left off with one really difficult problem here. It was just kind of a good exercise, but we tried to find the derivative of 1 over x plus 1. The same process is going to apply here. A lot of algebra going on, but I'll have you look at that kind of on your own. That's pretty much all we did today. So if you have any questions, feel free to send me an email. I know there's a lot of content here, so definitely don't be afraid to reach out, and I'd love to help you. I hope you have an awesome holiday weekend, and I will talk to you on Monday.